Hey everybody, this is Morgan coming back at you. More about bonding today. We're on page 6 of the outline. Okay? Now we're going to get into a couple of very important but somewhat challenging ideas. The first of which is formal charge. Now I'm going to write down this definition and you're not going to like it. I don't like it either, but knowing how to do it is different than liking the definition. The definition is the charge assigned to an atom in a molecule or a polyatomic ion also derived from a specific set of rules. Now, you can write that down, but I don't think it really tells you anything about what's going on here. Okay? Now, assigned. Does that charge really exist? Well, it does exist because of the distribution of electron density. But it's not our typical you've gained an electron or you've lost an electron. Okay? So what we're looking at is inside of a molecule. Where's the electron density? Is it more towards these atoms or is it more towards the other atoms? You calculate formal charge with V minus L plus 1/2 of the shared electrons. Now, let's kind of explain that. You take the number of valence electrons on the free atom, meaning when it's not bonded, minus the lone pairs, lone pair electrons, plus 1/2 of the shared electrons. So these are the electrons when it's a free atom. And these are the electrons assigned to it in a molecule. So, let's imagine the sulfate ion. Now, I think sulfate's a beautiful example for this. Sulfur bonded to oxygen. We'll do line structures. Sulfur comes in with 6, so 2, 4, 6, plus the 2 more from the negative charge gives me those. Coordinate covalent bonds to all the oxygens. Okay, now let's do a little calculation, because this Lewis structure here, to me, it looks beautiful. It's like, that's great. All the rules are followed. Okay, this just seems like a really likely Lewis structure. So sulfur, we're going to focus on the sulfur. We're talking about it. So the formal charge for sulfur, it has 6 valence electrons typically, minus. Now here, it has no lone pair electrons on it at all. So I'm going to say 0. Plus 1/2 of 2, 4, 6, 8 shared electrons. So that's 4. 6 minus 4 equals, I'm going to say positive 2. Now what that means is that the way I've drawn this structure, sulfur doesn't have enough electron density. So it's going to be pulled towards it. Electron density is going to be pulled in. How could that happen? Well, it could happen by forming a double bond. And when I look at that, I get the formal charge by saying 6 minus, still no lone pairs on the sulfur, and 1/2 of 10 2, 4, 6, 8, 10. So what does this equal? Half of 10 is 5, so that's a positive 1. So electron density is still going to be pulled towards the sulfur because its formal charge is positive. Well, sulfur could form 2 double bonds. That's possible. Okay, and this time 6 minus 0 plus a half of 12 equals 0. So that means that the electron density on the sulfur is where it should be. It's not attracting any more electrons in. Now, if I did 3 double bonds, this would come out to be -1, and if I did 4 double bonds, this would come out to be -2. And if the formal charges there come out to be negative, it pushes electrons away. If they come out to be positive, it pulls them in. There are really important implications for this in organic chemistry. Okay, so that's formal charge. You want closest to 0 for your central atom. Now we look at dipole moments. Okay, dipole moments help us to understand the concept of whether or not a molecule is polar. Okay, now we can't have a polar bond and we can have a polar molecule, and they're not the same thing. Okay, a dipole moment is a separation of charge. Now when I look at H2, that's the structure for it. Now that could be represented by this model right here. Now what's going on is that the electronegativities of both atoms are perfectly the same. So the pull of electron density is even in both directions. So no matter how I look at this, okay, the electrons are being evenly distributed in the bond. So the bond is nonpolar. Also, the molecule is nonpolar, meaning it does not have a dipole moment. Now let's change this up a little bit and let's do HCl, also a diatomic, except I know that chlorine is more electronegative than the hydrogen. So what we'd like to do is draw a vector above this, an arrow, and give the tail a little positive sign, saying that there's more electron density around the chlorines than around the hydrogens. It's a polar bond. It's got a polar covalent bond, and this is going to have a dipole moment. So we also say it's a polar molecule because the electrons are not distributed evenly. Now if I go back to this model, pop off one of the hydrogens, and in its place I'm going to put on a chlorine. Now I know the electron density is greater over here than over here. If I turn it around, that electron density has actually moved where it is. Instead of being on the left, it's now on the right. It's still associated with chlorine. Okay? So, when I have a molecule that's asymmetric, I know right away that I have uneven electron density. Now, biology books and very old chemistry teachers tended to draw a delta plus, delta minus, instead of using this arrow notation. But this arrow notation has been standard since before I was in school, so we're going to keep using it. Now, for BCl3, boron in the middle, chlorine, chlorine, chlorine. This is one of the reasons why I encourage model sets, okay? When I look at a model of this, I see that I have 3 equal sites here. And what's happening is the electron density is being pulled up towards that chlorine. It's being pulled over towards that chlorine. And it's being pulled over towards that chlorine. So I have 3 different pulls on the electron density. Except this molecule, and I'm spinning it like this deliberately. Okay, it's not a fidget spinner. It's to show you that all of these sites are equal. And what happens is that this distribution is even over the whole molecule. It has a polar bond. Yes, for sure. But it is a non-polar molecule because of its symmetry. Okay? Now, if you understand vectors, the resultant of these three vectors is 0. So I have no net separation of the charge. Now for NH3, I can look at this molecule. Okay? This model shows it nicely. I've got this lone pair up here on the nitrogen. Right away, I know this is going to have a dipole moment. It's going to be a polar molecule. See, if I turn it upside down, it looks different. If I turn it this way, it looks different. I can tell the difference. There is no real symmetry there inside this one. So this is a polar molecule. Okay? So it helps often to build models of these molecules to look at, to get a feel for whether or not there is symmetry to them and even distribution of electrons. So, a perfectly symmetric molecule has no dipole moment. Now, just to give you a comparison, okay, this is methane, CH4, and the bonding in ammonia is very, very similar, okay? If I turn this over, spin it, I really don't know that I have. I can't tell the difference. But if I turn this over, I can most definitely tell the difference. Okay, that was page 6. Thanks for tuning in, everybody. This is Morgan, signing off.